Have you ever stopped to wonder how an insurance company actually puts a price on your future? I mean, it seems impossible, right? A bit like looking into a crystal ball. And you know what? In a way, it is. Today, we're going to dive into the really elegant math that insurers use to turn the total chaos of life into the cold, hard numbers of risk.
And that's really the heart of the problem, isn't it? Insurance isn't just about one single event like death. Life is messy. It's this complicated journey with a million different forks in the road. So how on earth do you build a financial model that can handle all of that uncertainty? Well, let's break it down.
So what's the real challenge here? I mean, pricing a simple life insurance policy, that's relatively straightforward. But what happens when you start to factor in all the other things that can happen to a person? As you're about to see, it gets complicated, and it gets complicated fast.
Just think about these common policies. None of them are based on a single, clean event. They all depend on a person's health, which can change all the time. You might get sick, then you might recover, you might need long-term care. Every one of these possibilities is what's called a competing risk that the model has to somehow juggle.
So the bottom line is this: how do you put a dollar value on a future that isn't a straight line? You need a system that can handle all these competing outcomes, getting sick, getting better, and of course, eventually passing away. And it has to be able to handle them at any point in time. It's a massive puzzle.
So how do actuaries, who are basically the mathematicians of the insurance world, how do they solve this massive puzzle? Well, they use this surprisingly elegant framework that literally turns the chaos of life into a neat, orderly map. Let's take a look at how they build it.
The solution is something called a multiple state model. And really, it's just a flowchart for life's biggest uncertainties. It starts by defining the key conditions or states a person can be in, and then it just maps out all the pathways or transitions between them. It's a really powerful way to bring some structure to the unknown.
At its core, the model is just a simple map. It imagines your life as a series of connected points on a journey. So, for example, let's just think about the three most basic states of being when it comes to your health. You can be healthy, you can be sick, or you can be dead. The model just draws the possible pathways between them.
Okay, so let's break this down a bit. The states, those are the boxes we just mentioned. Healthy, sick, dead. Simple enough. The transitions are just the arrows, the pathways between them. But here's the secret sauce, the transition intensity. This is the calculated force, or rate, that measures how likely it is for someone to move between states, and it's all based on massive amounts of real-world data about people's health at different ages.
Okay, so we have this cool map of life. But how does a map turn into a premium that you actually have to pay? Well, this next step is all about connecting those probabilities to actual dollars and cents. Now, you're going to see a formula on this slide, an integral. Please do not panic. You do not need to be a math genius. We're going to focus on the simple logic behind it, not the calculation itself. The key idea here is called expected present value, which is really just a fancy way of saying what a future payment is actually worth in today's money.
And this just lays it out beautifully. To get to the price, you basically do four things. First, you use that model to figure out the probability of someone being sick at any given moment in the future. Second, you multiply that probability by the benefit payment. Third, you discount that future payment to find its value today, because, a dollar tomorrow is worth less than a dollar today. And finally, you just add up all of those possible discounted payments over the entire life of the policy.
And that's really the magic of it. All of this elegant math serves one very practical purpose. It takes this complex web of probabilities about our future health and boils it all down into a single concrete number, a price.
But here's the thing, building these models isn't just pure science. There's a real art to it too. The real skill is knowing exactly what you need to include and just as importantly what to leave out to build a model that's both accurate and actually useful.
So let's think about that for a second. Our simple healthy, sick, dead model is a great start, but what's it missing? What other real-life events could totally change whether an insurance company has to pay out a claim?
Well, a huge one is when people just stop paying their premiums. In the insurance world, this is called a lapse, and if a policy lapses, the insurance company is off the hook. Ignoring this possibility would paint a completely unrealistic financial picture.
And just look at the difference it makes. If you ignore lapses, you're basically assuming everyone keeps paying their premiums forever. This seriously overestimates how much the insurer will have to pay out. But by adding a lapsed state, the model gets much more realistic, giving a way more accurate valuation.
This all leads to a key idea in modeling called parsimony. It's kind of a fancy word, but it's a super simple idea. A good model should be as simple as it can be, but no simpler.
It needs to capture everything that's actually important for accuracy, but avoid any extra complexity that doesn't really add value.
This quote from the source material just sums it up perfectly. The whole game is finding that sweet spot. You include every pathway that has a real, material impact on the final number, and you just leave out everything else. For instance, adding a transition from lapsed to dead probably isn't going to change the sickness benefit calculation, so you just leave it out.
Now, not every situation needs a model where you can move back and forth between states. Sometimes life is more of a one-way trip, and for that, actuaries use a special, much simpler type of model.
It's called a multiple decrement model. And the idea is you start in one active state, like say being an active member of a pension plan, and you can only leave for different absorbing states, like retirement or death. Once you're out, you can't come back. It's the perfect tool for modeling these one-time events.
Okay, here's a really subtle but incredibly important question that shows you just how precise these models can be. Think about it for a second. Does getting sick during a year mean the same thing as being sick on the last day of the year? It sounds like it might, but in the world of competing risks, it's a definite no.
Here's the crucial difference. The probability of leaving the healthy state counts everyone who got sick at any point during that year. But the probability of being in the sick state at the end of the year is actually lower. Why? Because death is a competing risk. Some of those people who got sick during the year might have actually died before the year was over. The model's ability to tell these two things apart is what makes it so powerful.
So if there's one thing to take away from all this, it's that these multiple state models are so much more than just equations. They are a powerful and flexible language. They give us a structured way to talk about and to financially value all the complex, uncertain, and tangled up pathways of our lives.
And that leaves us with a pretty fascinating final thought. We now have these amazing tools to map the competing risks of our health and our finances with incredible precision. It really makes you wonder, what other complex, uncertain parts of our future are we going to start to model next? Thanks for joining this explainer.